Hey, hello everyone. Thanks for
Hello.
your hello.
Hello. Ichigo
Hi.
Kanachiro from the IK.
Oh, nice to meet you. This is Wentao Luo, the chair of this session. Thank you for your participation. I think our first speaker is not showing up now. So our next speaker is Sarah. Sarah, are you here?
We still have 10 minutes or 8 minutes. Maybe first speaker will appear.
Yeah. So we met some problem last time, not yesterday, the day before yesterday. So one of the first speaker cannot share the screen successfully. So I'm thinking maybe we can try
Can I try to share my screen before we start, please?
Yes, of course. Please go ahead.
Just to be sure that everything works fine. So seems to be all right, right?
It's perfect. Thanks, Igor.
Okay, fine. So I unshare.
Yep.
Stop sharing. Thank you.
So are there any other speakers that want to test the sharing system?
Yeah, sure. I would like to try it. So
Yes, please, Miguel.
is it showing the presentation?
Not yet for me.
Okay, try it again.
Sarah
Now?
here. You can.
Yeah, this
So
yeah, it's perfect. It's working now.
Okay.
It's working now. Yeah.
Okay, thanks. So let me just stop share.
So again, now for the newcomers, we are testing the sharing systems because we met some issues the day before yesterday. So if anyone who wants to test the sharing, please go ahead. We still have 6 minutes for the testing.
Okay, can I test my?
Yes, Sarah, go ahead.
Okay, yeah.
Perfect. Quantum dynamics.
Yeah, can you see if all of this, like the
Yes.
transitions? Okay, perfect.
The animation.
Thank you.
Great, thanks. So anyone else, the speakers who wants to share the screen to test the sharing? Yes, yes, please.
Can you see it?
Yes.
Okay.
Perfect.
Thank you.
Yep. Yep. Who's sharing now? Shahab. Yeah, I can see your screen. That's it's working. That's great. Thanks. It seems that the system works well today. So let's wait for another 4 minutes and start the meeting. So, but during this period of time, 4 minutes, if there's still some speaker who hasn't tested the sharing system, please go ahead. Feel free to test the system.
Please, can I test the sharing?
Oh, yes, please.
Does it work?
Can you try presentation view? How to say? Yeah, it works.
Okay, thank you.
Perfect. Thank you.
Good morning, everyone.
Hello, Manus. can you try to share the screen and test the system?
Sure, sure. Let me. Okay.
Yeah, great. It works.
Okay. Let me.
So we still have 3 minutes to go. So I'm wondering if there are still speakers haven't tested the sharing system. If no, I think Manus, you can stay the
Okay.
sharing state because you're going to be the first speaker.
Yes.
And 2 minutes to go. I think there are 2 minutes to go, but I think if you don't mind, we can start a little bit earlier. Hello, everyone. Yeah, so I'm going to use 1 minute to introduce myself, and also thanks for all your participation. I'm Wentao Luo. I'm going to be the host of this session. This is going to be the last day of this fantastic MG16 meeting. Thank you all for your participation. The talk will be, each talk will be a 15 minutes talk plus 5 minutes question time. So our first speaker is going to be Emmanuel Saridakis, and take it away.
So thank you very much for this nice introduction. And of course, I thank the organizer for the invitation to give this talk in this nice section. So very briefly, because we don't have enough time, we are going to present the teleparallel and FT and in general the torsional modifications of gravity, which is a quite hot subject recently. So the goal is to investigate cosmological scenarios in a universe governed by torsional modified gravity. As you know, there are many models of modifications of gravity in the literature. Usually, most of them arise if you add extra fields in the Einstein-Hilbert Lagrangian, or extra fluids, or if you go to higher derivative terms like in f(r) gravity, or in scalar vector tensor theories, like in Galilean and Hordensky theories. We are going to focus on a more radical modifications of gravity, which is to change the underlying geometry. So to change the geometrical frameworks of the gravitational description, and this is done through torsion. Now, what is the basic point? And as I can see, many of the audience have an experience with torsional gravity, but let me summarize. In general relativity, Einstein had the basic idea that gravity is geometry. Geometry is curvature, so gravity is curvature. As Wheeler beautifully says in his book, in general relativity, matter tells space-time how to curve, and the curve space-time tells matter how to move. So technically, in general relativity, one uses the Levi-Civita connection, which by definition leads to zero torsion. So all the gravitational information is embedded in the curvature tensor. However, 10 years later, it was Einstein himself that found a completely equivalent way to describe gravity through torsion. Initially, his motivation was the following: curvature to describe gravity, torsion to describe electromagnetism, so he could have in geometrical terms using both curvature and torsion and unified description of gravity and electromagnetism. But in the end of the day, he found that torsion does not describe electromagnetism. Torsion is just an alternative equivalent way to describe gravity. So in torsional formulation of gravity, in the so-called teleparallel formulation of gravity, gravity still is geometry, but geometry is torsion, so gravity is torsion. Technically speaking, one uses the Weinberg connection, which has zero curvature, so all the gravitational information is embedded in the torsion field. Now, I want you to understand, here is one of the take back home messages, the following. Curvature and torsion are properties of the connection, not properties of the space-time. If I give you a space-time, a specific space-time, and I'm asking you, what is the curvature and torsion of this space-time? What is the answer? The answer is that there is no answer. If I need to calculate curvature and torsion, I need to define the connection. You see, the metric comes from the Greek word to measure. It helps you to measure areas, angles on the manifold. But the connection is related with a completely independent concept, which is the concept of parallelism. The way you define your parallel transportation is completely independent from the way you define your metric. So, curvature and torsion are properties of the connection. There are infinite choices of connections. Amongst them, there is only one, Levi-Civita, that has zero torsion. And there is a Weinberg connection which has zero curvature. So, in this kind of theories, usually one uses the tetrad field. So the dynamical variable is the field bind field, which is the orthonormal vectors on the tangent space, and they are related to the metric with this known expression. So one applies the Weinberg connection, and then he defines the torsion tensor according to this expression. So in general relativity, all the gravitational information is embedded in the curvature tensor, the Riemann tensor. But in teleparallel gravity, all the gravitational information is embedded in the torsion tensor. In general relativity, one uses contractions of the Riemann curvature tensor to find the Ricci scalar, which will be the Lagrangian of the theory. And here we are using suitable contractions of the torsion tensor to construct the torsion scalar T, and this will be the Lagrangian of the theory. And as you know, if I use this Lagrangian and I perform variation in terms of the tetrads, I obtain completely equivalent equations with general relativity. So that's why this theory is called teleparallel equivalent of general relativity. Now, GR is completely equivalent with the teleparallel equivalent of GR. However, let us go to modified gravity. In curvature gravity, one simple modification is F of R gravity. So let's play the same game here and go to F of T gravity. The interesting thing, and this is the second thing I want you to take back home, is that although GR is completely equivalent with teleparallel equivalent of GR, their modifications are not equivalent anymore. So F of R and F of T gravity correspond to different classes of gravitational modification. So that is why it's worthy to study them. These are the equations of motion in general, and if we want to do cosmology, we assume a homogeneous and isotropic universe, and these are the Friedmann equations. As you can see, the Friedmann equations are different comparing to F of R. So it's a novel modification of gravity. And in FRW geometry, the torsion scalar is -6h squared. So you can see from here the important advantage of F of T gravity, that the field equations are second order, while in F of R gravity, the field equations are third order. So if you want to do cosmology, from the Friedmann equation, you can define an effective dark energy density and sector of torsional gravitational origin. And this is the equation state parameter. So you have a rich freedom to do cosmology, and you can explain the late time acceleration, inflation, etc. And you can also do perturbations. Now, in a similar way, inspired by curvature gravity, in curvature gravity, apart from F(r) gravity, as I told you in the beginning, you can start introducing a scalar field non-minimal coupled to gravity, so to the rich scalar. So you can do the same thing in torsional gravity and introduce a scalar field non-minimal coupling to torsion. Again, you can extract the Friedmann equations, and you can see that non-minimal torsion gravity, in the literature we call these theories now scalar torsion theories, similar to scalar tensor theories of curvature. This theory, non-minimal torsion gravity, is different than non-minimal curvature gravity. You can see from the Friedmann equations. And also this is reflected to phenomenology. In non-minimal torsion theory, you can obtain the phantom regime, which is not possible in non-minimal quiescences. So you can see again that torsional gravity gives you richer possibilities. As you know, again, in curvature gravity, one can go and study higher order curvature modifications, like the Gauss-Bonnet combination. So the question is, can you do that the same thing in torsion gravity? Yes, we did that in a series of papers. And here, okay, don't pay attention to the details, K is the cotorsion, but yes, you can construct the telepara equivalent of the Gauss-Bonnet theory, and then you can go to F of t, Tg theories in a similar way, where you have F of r, G theories. So you have the telepara equivalent of Gauss-Bonnet theories. And again, these theories prove to have very interesting phenomenology, and they can give you inflationary solutions and late time accelerated solutions. You can proceed, again inspired by curvature gravity, and consider higher order terms like nabla of torsion and box of torsion. I don't give the equations here, but the phenomenology is in agreement with observations, and you obtain the thermal history of the universe. And also you can use the boundary term B. The boundary term is the difference between R and T, because R is equal to T plus a boundary term. But you can play with this boundary term in modifications of gravity as well. So this is a map from Bahamoder-Bemer's paper that here is the general, say more or less, one of general torsional gravities. You have T, B, T, G, the boundary term of the Gauss-Bonnet, and the trace of the energy momentum tensor. And by taking zero of some quantities, you go to various subcase. And of course, at the end of the day, when your theory is just linear in T, you obtain GR or TGR. Okay? And this is just to have in mind the geometric foundations that in general, a general connection can have curvature, torsion, and non-metricity. So you can play with all this and have all combinations. You can have, for instance, the Riemann-Cartan geometry, in which has zero non-metricity. You can have torsion-free geometries, and you can have teleparallel geometries. So the Riemannian geometry that you are all familiar with corresponds to zero non-metricity and zero torsion. Teleparallel gravity corresponds to zero non-metricity and zero curvature, the Weisbach gravity. And in the literature, you can find the non-metricity gravity or symmetric teleparallel gravity that corresponds to zero curvature, zero torsion, but not zero non-metricity. And of course, if everything is zero, you go back to Minkowski. Now, let us see what observations are telling us. Of course, the interesting thing, as we are all familiar with, is to study perturbation in this theory, because perturbations determine you both the large-scale structure of the universe as well as the CMB details. So in a general theory, the perturbation equation sub-horizon level and under assumption of matter domination is given by this expression. And you can parameterize here the matter of density delta through the growth index gamma. Now, the important thing is that in modifications of gravity, all the information of the gravitational field is embedded in this effective Newton's constant. So in F of t gravity, the effective Newton's constant is given by this expression. So this carries all the information. So if you use observations that constrain the growth index and the large scale structure, you can constrain F of t gravity itself. So here are observational confrontation at the background level and here at the perturbation level. And you can extract constraints on F of t gravity. And again, in a series of works in the literature, one can find the observational constraints using supernova type 1, baryonic acoustic oscillations, cosmic chronometers, CMB, and all kinds of data that constrain you F of t gravity. So F of t gravity is in agreement with observations. Now, a different approach that we followed also with Professor Chai is to use Gaussian processes in order to reconstruct F of t gravity in a model-independent way. So you take the late time data and you reconstruct the Hubble function and h dot, and in the end of the day, F of t, without any other assumption. And we have some parameterizations that fit the data the best way. Now, what is very important to mention here is that F of t gravity is able to elevate the two famous tensions that exist in standard cosmology, which is the H0 and sigma 8 tension. Very briefly, H0 tension tells you that the Hubble rate that is indirectly estimated through Planck measurements, assuming lambda CDM cosmology, is different from the Hubble rate that we observe locally through the CFITs. And actually, the local estimation is higher than the one indirectly estimated by Planck. Now, sigma 8 tension, this quantifies, the F sigma 8 quantifies the root mean square time-dependent fluctuations of the matter of density inside spheres of radius 8 megaparsec. So there is a distribution of matter. This is the large-scale structure. And actually, there seems to be less clustering than predicted by lambda CDM. So this is a sigma 8 tension. And F of t gravity is one of the few scenarios that can solve both tensions at the same time. Why? Because in F of t gravity at intermediate times, gravity is weaker. So what does it mean, weaker gravity? It means, first of all, faster expansion, right? And less clustering. So with F of t gravity, you can elevate the tensions at the same time. And of course, one should use early universe data, so from Big Bang nucleosynthesis, and also investigate the baryon and baryon asymmetry in order to impose constraints on F of t gravity coming from the early universe. In another work we did with the Hefe USTC collaborators is to use galaxy-galaxy lensing in order to constrain F of t gravity. And we were able to propose a parameterization, so a deviation from lambda CDM cosmology. So here T is just a telepar equivalent of general relativity, general relativity. Here is the cosmological constant, and we propose a constant, a deviation from lambda CDM, a power law, which is consistent with the data. And of course, the last thing that we are doing recently is to use gravitational waves in order to constrain torsional gravity, because as you know, we have many events right now and much more, many more are expected the following years. So the idea is you investigate the torsion tensor perturbations and you find the effect of torsional modified gravity on the equation of the gravitational waves. Again, this is in collaboration with Professor Chai's group in USTC. And we found, first of all, that gravitational waves in f of t gravity propagate at the speed of light. This is very good result because it helps you to bypass the results from the gravitational wave observations that the gravitational waves propagate at the speed of light. So they easily pass this constraint, and there is, of course, a modification in the dispersion relation. So what we are doing is the following. You take models of torsional gravity and you find the effects on the gravitational wave profile. And there is a difference, and through this difference, we expect to be able to confront the theory. And of course, you can do that in other torsional gravities like in f of tb. So let me conclude. Torsional modified gravity is very efficient in doing cosmology. I want you to have in mind that even if we accept Einstein's main idea that gravity is geometry, we are not necessarily restricted to Riemannian geometry. Riemannian geometry was a simple geometry that Einstein was familiar with, but at the time that general relativity was being built, there was no other geometries. Torsion came into the game after 1919 with the works of Weinsbach, Cartan, Poincaré, and the others. So Einstein didn't know torsion in 1915. But when he learned about torsion, he understood that geometry is much richer and we can formulate geometry using torsion. So gravity can be described equivalently by torsion. So since we are modifying gravity today using curvature, a new way that is worth it to investigate is to put into the game torsion. And f of t gravity is the simplest example, but you can have other forms of torsional gravity using higher order invariants, boundary terms, scalar torsion theories, etc., etc. I'm not saying that this is the correct modification of gravity and the curvature gravity is wrong. All I'm saying is that these are different classes of gravitational modifications and it's worth it to study them. And with our group, we are investigating that and we are getting prepared for the huge flow of data that are going to come in the near future concerning both the large-scale structure in the CMB, but also on the gravitational wave. We need to get ready. So I finish here with a famous label that was in Plato's Academy, the first university in the world. Actually, it was very near my house here. So although this was a general university, on the door, it was written that those who don't know geometry are not allowed to enter, meaning to say the crucial important role of geometry in the underlying framework of knowledge. So I thank you here, and just to make an announcement, as you know, in Corfu, in Greece, we're organizing some European conferences and schools from some networks of 30 countries that we participate, and you are all familiar to physically come and join. So thank you very much. I stop here.
Thank you, Emmanuel. Thank you for your crystal clear talk about the geometry, the beauty of geometry. I think, sorry, due to the time limits, I think we don't have time for the questions, sorry. So we are gonna move to our next speaker. Manis, please stop sharing. Our next speaker is gonna be Sarah Uria. Can you share your screen, please?
Yeah.
All right. Please take it away.
Okay, 1 minute. Okay, good morning. First, thanks to the organizer for accepting my talk. I am Sara Fernandez Uria, a PhD student at the University of the Basque Country. And in this presentation, I am going to explain my work with David Brizuela, my supervisor, and Ana Alonso Serrano, which is focused on the study of quantum corrections to the Bianchitou transition. Our further results on the subject are gathered in the following paper, soon to be published in Physical Review D, and therefore I will base my talk on it. And naturally, you can check it for further details. Well, the structure of the presentation will be the following. First of all, I am going to give a brief introduction to contextualize our project. Then, in order to keep the talk as self-contained as possible, I am going to present the classical Bianchitou model and specifically its transition. Then I am going to describe the quantum dynamics and explain the quantum corrections that we have obtained for the aforementioned transition. And finally, I will bring this presentation to an end with the most relevant conclusions of our results and our future goals. Okay, so let's start. The Bianchitou model presents a cosmological singularity. Moreover, as the system approaches this singularity, it undergoes a transition between two Bianchi-1 models. Well, this is indeed a very well-known dynamic, but in the present work, we try to analyze how this classical transition is modified when quantum effects are considered, which are supposed to be relevant near the singularity. Well, many of you may not be familiarized with this model, so let's start by presenting it. Well, the Bianchitou model is spatially homogeneous, but not necessarily isotropic for dimensional spacetime. If we follow the AT1 formalism to describe it canonically, its Hamiltonian constraint in vacuum is given as follows, where here alpha describes the spatial volume and beta plus and beta minus are the shape parameters that describe the spatial anisotropy. Well, these are called the Misner variables, and P alpha, P plus, and P minus are their corresponding conjugate momenta. Well, if alpha is chosen as the internal term, the physical Hamiltonian of the system takes the subsequent form. Well, this is the most general description in vacuum, but in order to further simplify the problem, we can remove 1 degree of anisotropy, which is known as the locally rotationally symmetric case. And as you can see, in this case, the physical Hamiltonian is simplified as follows. Well, as mentioned, this model presents a singularity, even in this particular simple case, and more specifically, when alpha tends to minus infinity. Hence, it can be interesting to study the evolution of the model towards this limit. And for this purpose, the first step would be to obtain the equations of motion. Here, we remark that when this exponential term is negligible, P is a constant of motion. That is, the system follows a free dynamic. Well, during this period, the Bianchitou model is equivalent to a vacuum Bianchi-1 or Kastner solution, and thus it is said to be on a Kastner regime. For instance, if we begin our evolution in one of these regimes with positive P and large values of beta and alpha, we observe that as the system approaches a singularity, that is, as alpha tends to minus infinity, the shape parameter beta starts decreasing, but only up to a certain point where the exponential term stops being negligible, and therefore the Kastner approximation does not hold. At this point, a transition happens, and then the system enters in another Kastner regime, as you can see here. But well, how are these two regimes related? Well, a useful trick to study the transition is to exploit the constants of motion of the system, which are found to be these two. Well, if we evaluate these conserved quantities in these initial and final regimes, that is before and after the transition, and equate their values, we get a system of equations, and after solving it, we obtain the law that describes the transition between this initial and final regime. And well, here I must note that elements with tilde refer to the final state, that is after the transition. Well, once that we have provided the canonical description of the classical model, we are ready to develop the quantum analysis. Well, the quantum dynamics are governed by the following Hamiltonian operator, which is defined from the classical ones and chosen to be Ryle order. That is, with a totally symmetric ordering of the basic operators, beta and p. Then, instead of studying the evolution of the wave function itself, we follow a formalism developed for quantum cosmology and well, quantum mechanics in general, which is based on the moment decomposition of the wave function and the study of their evolution. Thus, according to this formalism, the system is fully described by the expectation value of beta, of p, and the following infinite set of quantum moments instead of by the wave function. And the order of these quantum moments is defined as E plus J. Well, the evolution of these variables is ruled by the following effective Hamiltonian, which is defined as the expectation value of the Hamiltonian operator and performing a Taylor expansion around the expectation values of beta and p. And that's why it can be written as this infinite series of moments. Well, this effective Hamiltonian encodes the complete dynamical information of the system. And in fact, the equations of motion of all of the variables of the systems, the ones that I have shown previously, are obtained as follows. Where here the Poisson bracket for expectation values is defined in the usual way, that is, in terms of the commutators. Well, here it is very important to emphasize that the evolution of these variables is completely equivalent to that given by the Schrödinger picture of the wave function. Well, once that I have clarified this, we observe that the classical Hamiltonian is not a polynomial, which means that the infinite series in the effective Hamiltonian is not truncated. Thus, the equations of motion form an infinite set of coupled equations. Therefore, in order to study and compute the dynamics, some kind of cutoff must be applied. For instance, to consider that all of the moments of order higher than a certain value n vanish. And in fact, such a truncation corresponds to considering a semi-classical regime, where the quantum state is picked on a classical trajectory, and hence all of the high order terms are negligible. Nevertheless, even if we apply a cutoff, instead of trying to solve this coupled system of equations for any value of alpha, we will focus on the so-called Kastner regimes, as we have done in the classical analysis. And that way, we obtain the following simple solutions. If we compare these results with the classical ones, we remark that the behavior of beta and p remains identical in the quantum analysis. Moreover, the moments show a very simple behavior since they hold a constant value. Then, once that we have characterized these quantum Kastner regimes, it can be interesting to study a possible transition between two of them. And for this purpose, we will follow the same procedure as in the classical analysis, which, remember, is to exploit the constants of motion. In the quantum scenario, the conserved quantities are these expectation values, where here R1 and R2 are the operator counterpart of the classical conserved quantities. And in fact, any of these combinations is also a constant of motion. Well, here, as a technical subtlety, it must be mentioned that the ordering of these operators is far from trivial, since for each order of the truncation, one must find the proper ordering so that they are conserved. And nevertheless, to higher orders, there may appear some terms that go with H bar, but still there's not an exact algorithm to obtain this correction. Well, once that we know the conserved quantities of this quantum model, based on the classical analysis, we will consider that we have an initial Kastner regime, and then as the system approaches the singularity, that is, as alpha tends to minus infinity, the system enters in another Kastner regime. Thus, if we evaluate the conserved quantities that I have just shown in these two regimes and equate them, once again, we get a system of equations, and after solving it, we get the quantum transition law, which is given as follows. Well, once again, I must note that elements with tilde refer to the final state, that is, after the transition. Well, on the one hand, we observe that the transition law for P remains identical. However, we obtain some corrections for that of beta, where here capital N, remember, denotes the order of the truncation. Still, as you can see, and as expected, if all of the moments are set to 0, we recover the classical transition law. On the other hand, the transition law for all of the moments can be written in this compact form. And up to fifth order, we have obtained in a closed form and analytically the exact expressions of all of these coefficients. Well, if we analyze this formula in detail, we remark that it is linear in all of the moments, except of some quadratic terms that go with pure fluctuations of P. Moreover, we also observe a strong dependence on the index of beta that determines which kind of initial moments affect the value of a given final moment. And here I must note that this result is independent of the order of the truncation and therefore physically meaningful. And well, to illustrate this behavior, I show here some examples up to fifth order. Well, once that we have studied the asymptotic characteristics of this quantum model, that is in the Kastner regimes, we have performed a numerical analysis to study its dynamical part in detail. And for this purpose, we have chosen an initial Gaussian state. This numerical study shows very well that at first, at high values of alpha, the system is in an initial Kastner regime. And then, as it approaches the singularity, it undergoes a transition. This transition takes place in a very, very small period of time, and then the system reaches very quickly its final equilibrium value, which, remember, corresponds to a new Kastner regime. Well, concerning the evolution of the variables beta and P, we conclude that they remain almost identical as in the classical analysis. And in fact, only in a very close sum into the transition at very small values of alpha, we can appreciate slight modifications. And for instance, we plot here the evolution of beta during the transition. And as you can see, quantum effects increase slightly the value of beta during this period. Moreover, concerning the evolution of the moments, we observe that at first they hold a constant value in the initial Kastner regime, and then as they approach to the singularity, they experience an excitation and start to grow exponentially. And then during the transition, they oscillate, but then they reach their final equilibrium value very quickly. And here we have plotted the evolution of the third order moments to illustrate this behavior. Well, in general, the precise dynamics of all of the moments are quite complex, but if we look into the transition in more detail, there are some general features that we observe. And to explain these characteristics, we show here the evolution of the second and the third order moments. For instance, we see that lower the order of the moments, sooner they start to oscillate and with bigger amplitudes. And this is, in fact, in agreement with the semi-classical hierarchy of the moments that we are assuming. Moreover, we observe that at its given order, pure fluctuations of P have the biggest amplitudes. As you can see here, the purple one, and also here, the purple one. And higher the index of P, sooner they reach their final equilibrium value. As you can see, first of all, the purple one, then the blue one, and finally the orange one. And for the third order moment, similarly. First, the purple one reaches its final equilibrium value, then the black one, then the orange one, and finally the blue one. And furthermore, in general, moments with at least one odd index, for instance, all of the third order moments and this blue one, present more oscillations. As you can see, all of them have in here 2 oscillations. This blue one also, while the other ones that don't satisfy this condition, don't have at least one odd index, have only 1 oscillation. And in fact, this is an interesting feature since these moments, the ones that have at least one odd index, are initially vanishing due to the choice of the Gaussian state. But then, thanks to this oscillation, they can reach a final non-zero equilibrium value. But what does this mean? Well, that states with no initial correlations between beta and P develop non-zero correlations after the transition. And well, to conclude, we have described the LRS Bianchitou model in the moment formalism. And more specifically, we have studied in detail the asymptotic or Kasner regions. Then with the constants of motion that we have found, we have fully integrated the equations of evolution. Then, making use of these conserved quantities, we have obtained analytically and in a closed form the exact transition law for all of the variables of the system up to 5th order, which remember corresponds to neglecting terms of order h bar to the power of 3 and higher. And furthermore, with the numerical analysis, we have studied the dynamical part and mainly the period where the transition takes place. Then the follow-up of this work could be, first of all, to remove the LRS symmetry and, well, to study the most general Bianchitou model. Then the next step could be to extend this analysis to the Bianchi-9 model, which can be understood as a succession of Bianchitou models. And ultimately, our main goal will be to obtain the quantum corrections to the BKL transitions. And well, that will be all. Thank you very much for your attention. And please feel free to ask any questions. And also, if you want to check our paper on arXiv, feel free to do it to see all of the details.
Yeah, thank you for your nice talk. And I don't think there's a time for questions. People who have questions, please send the direct message to Sarah via the chat channel. So Sarah, could you please stop sharing? And our next speaker is going to be Shahab Shahidi. Please start sharing your presentation. Shahab, can you hear me? I can see your screen, but not the presentation. Yeah, great.
but we cannot hear him.
Yeah, I think you are muted. Shahab, are you muted? We cannot hear you. It says it seems that there is some kind of problem with the audio system.
His audio system is not working.
Exactly.
No.
Can you speak up? Can you try it again? Interesting. Shahab, can we move you to the next speaker so that we can save? Do you mind that we move you to the next speaker? Shahab, can you hear us? I can see you. I can see you. If the system is not working well, could you please stop sharing and test your system so that we can move on with another speaker?
Sorry, can you hear me now?
Great. Yes, we can
Yes.
hear you now. Yeah, great. Please open up your presentation.
Hello.
Hi. Can you hear us? It's a bit choppy.
Hear me? Hello?
Could you please share the screen? I'm wondering if it is my problem or Shahab's connection problem. Shahab, can you hear me?
Yeah, yeah, I can hear you. Could you hear me?
Yes. Please share your presentation and start the talk.
Okay. Sorry for. Could you see my screen?
Yes. Perfect. Take it away.
Okay. Thank you very much for the organizers, and I'm very glad to be here. I'm going to talk about late-time cosmology with derivatives of matter Lagrangian. This work is in collaboration with Zahra Haqqani. First of all, I will give you some motivations that why we should add some derivatives of matter Lagrangians to the Einstein-Hilbert action. And then I will present you a simple model. I will consider two separate models, actually, one with cosmological constant and the other without cosmological constant. And we will see what cosmological implications of these two models are. We will consider the background cosmology and dynamical system analysis, and I will give you a very little comment about the Hubble tension in this model. The accelerated expansion of the universe is one of the interesting things we have in the last decades, and this and all the observations are mainly explained by the so-called Landau-Sidia model, which has a cosmological constant term and cold dark matter. But we all know that this Landau-Sidia model has some problems, something like the cosmological constant problem or Hubble and sigma intentions, and etc. So it is very interesting to investigate some alternative theories of gravity beyond Landau-Sidia to relax or at least compensate the effects of the cosmological constant. As Emmanuel has commented in his very interesting talk, there are plenty of alternative theories of gravity which all try to do the same thing. But here my idea is to add some derivatives of matter Lagrangians to the Einstein-Hilbert action. Very simply, we can think that the evolution of the non-relativistic dust pressureless matter source with respect to redshift I plotted here is as you can see at redshift near 0, this plot is nearly flat, and the derivatives of this function is nearly constant. So if we can add some derivatives of energy density to the action, this can play the role of the cosmological constant. This is what we are going to do in this talk. The action we are considering here is, you can see here, the first part is the Einstein-Hilbert action with the cosmological constant. The second part, the red part, is the new term, which has derivatives of matter Lagrangians. F is an arbitrary function of the matter Lagrangian. I will study the baryonic matter, the perfect fluid, which matter Lagrangian is equal to minus the energy density of the fluid. So these are the derivatives of the energy densities. And alpha here is a dimensionless constant. You can see that I add only the standard kinetic term of a scalar field because F is a scalar field, but it has some internal matter structure here. So this differs from a scalar tensor theory, as we can see in the next slide, but I should note that this theory is not equivalent to F of R and LM theory. The equation of motion of this action can be obtained as you can see here. The black parts are the standard Einstein terms. Here in the second line we have the equation of motion of the standard kinetic term of the scalar field, but this in the first line, this green term is what we have if the scalar field has internal matter structures. You can see that extra energy momentum tensor and Lagrangian is appearing in the equation of motion. Because we have added some extra matter fields to the action in a non-standard form, the energy momentum tensor in general is not conserved. And one can obtain this non-conservation of the energy momentum tensor. You can see here, if alpha equals to 0, we restore the conservation of the energy momentum tensor. This is the alpha term is related to our new term in the action. But there is a very interesting thing here. If we study, if we assume that the matter has a perfect fluid structure, one can obtain this non-conservation equation in this form. And H here is the projection tensor, which projects tensors to a hypersurface orthogonal to u mu. And on top of FRW spacetime, everything depends on time, and derivatives are orthogonal to u mu. So the right-hand side of the non-conservation equations cancels, vanishes in the FRW spacetime, and in a background FRW spacetime, we restore the conservation of the energy momentum tensor. This is not the case for other non-minimal matter curvature coupling theories, something like F of R T or F of R and L. Before I go to the cosmology part, let's talk about the weak field limit of the theory. In the Newtonian limit, the line element is a linear order perturbation of the mean Minkowski space. Here, phi is the Newtonian constant, Newtonian potential, and only the energy density remains in this limit, and the pressure terms are of higher order in perturbation theory. If we assume that the function f is a smooth function, we can expand this in terms of powers of the energy density rho, and since f appears at least at least twice in the equation of motion and also in the action, and rho is the perturbative term, there is no contribution from this new term in the Poisson equation. So we, at linear level, we recover the standard Poisson equation in the Einstein theory. Okay. Let's talk about the cosmology of the model. I will assume a simple form of a power law for the function f, as you can see here, and by calculating the Friedmann equation, we can obtain the Hubble parameter in this form. The first part is the standard Landau-Cillian form. The second part is a new part, which you can see that it's related to the derivative of the matter Lagrangian. Here, R is the sum of rho m and rho r, rho bar m and rho bar r. These are dimensionless quantities related to the dust and radiation energy densities. And I also define the cosmological constant abundance. We will consider, as I said before, two separate cases. One case, we have a cosmological constant, and the other, the cosmological constant is said to be 0. If you remember, the matter sources are conserved, so the dimensionless energy density of dust and radiation behave similarly to the Einstein theory. In redshift coordinates, the Hubble parameter could be written in this form. The new term is here in the denominator of this statement. If the cosmological constant presents, we can obtain from this equation the cosmological constant abundance in terms of dust abundance and also beta term. This is because we scale the Hubble parameter here with today's Hubble value h naught. So if we set z equal to 0, small h should be 1, and we can obtain this relation. In the vanishing cosmological constant case, we can obtain beta from this equation in terms of the dust abundance. Okay. For both models, I have estimated the best fit parameters of the model. This is for the non-vanishing cosmological constant case. H naught is equal to 65, which is very similar to the Landau-Cillian value, but the dust density abundance is 10% larger than its Landau-Cillian counterpart. And beta term is, you can see that it is always positive up to 1 sigma confidence level. The cosmological constant abundance here can be calculated to be 0.59, which is 10% smaller than the corresponding Landau-Cillian value. So this specific model can compensate the the effect of cosmological constant at least by 10%. In the vanishing cosmological constant, it is interesting because H naught is shifted to approximately 70, which makes the Hubble tension better for the vanishing cosmological constant. And here the n, which is the power of the function f, is estimated at best value to minus 0.21. And beta can be obtained from these estimated values to be minus 0.42. Okay. I have plotted the Hubble parameter and the deceleration parameter for the non-vanishing, for the vanishing cosmological constant term. You can see that the observational data on the Hubble parameter is fully addressed in this theory, in this model. Let's talk about dynamical system analysis of the model. In the vanishing cosmological constant case, we have 3 dynamical variables. One of these can be obtained from the Friedmann equation, so the system is 2-dimensional. And for the non-vanishing cosmological constant case, we have 4 dynamical variables, which omega lambda can be obtained from the other 3. And in this case, we have a 3-dimensional dynamical system. I have plotted the evolution of matter, radiation, and dark energy abundances in terms of e-foldings. You can see that the qualitative behavior of the models are the same as the lambda CDM. The dashed line here is the lambda CDM model. The dotted are for the non-vanishing cosmological constant. The solid line is for the vanishing cosmological constant case. For the non-vanishing cosmological constant, the matter radiation transition occurs earlier than the other two. The vanishing cosmological constant case has 2 fixed points related to the matter and radiation fixed points, which you can see in this plot. And here we don't have any Dositter fixed point, but a stable manifold passing from the origin. In this black solid curve related to the Dositter behavior, closer to the origin, we have more acceleration. So this is more like a phantom behavior. Not Dositter behavior. But the overall behavior of the universe could be followed from radiation-dominated point, which is unstable, to the matter-dominated fold, which is a saddle point, and then goes to the accelerated expansion phase. For the non-vanishing cosmological constant case, we have 3 fixed points related to the radiation, matter, and Dositter points. And everything here is similar to the lambda CDM model. Only the only difference is that here we have a 3-dimensional dynamical system. I have plotted the omega h equal to 0 slice, which where radiation and matter fixed points are present there. But the Dositter node is a fixed line here. Both of models can actually explain the history of the universe in this manner. In conclusion, I should say that derivatives of matter Lagrangian could be considered as an alternative theory. of gravity, and we can add higher order terms like Galilean terms to make the Hubble tension better. And we should and we have considered the first order perturbative analysis of the model, and the sigma 8 tension is also addressed here, but I don't I haven't time to discuss that in this time. Okay, thank you very much for your listening.
Thank you, Shahab. If you have any questions, and please send the message through the chat channel. Shahab, could you please stop sharing your screen? And our next speaker is going to be Eleonora Giovanetti. Please share your screen. Hello?
Hello, yeah.
Could you please start sharing your screen?
Yes. Can you see the screen?
Yes, perfect. Please go ahead.
Okay. Good morning to everyone. Today I will present this work entitled Semi-Classical and Quantum Features of the Bianchi's First Cosmology in the Polymer Representation. That is the result of the collaboration of the authors written here. The presentation will be divided into several sections. Firstly, I will present polymer quantum mechanics and the classical dynamics of the Bianchi's first model in the Geodesic variables. And then I will move on talking about the core of the article, in which we apply polymer representation precisely to Bianchi's first model. So I will firstly present the semi-classical dynamics in the Geodesic variables and in the volume-like ones. And then I will present the generalized version of the Friedmann equation for this model in the polymer representation. Finally, I will talk about the quantum analysis in the Geodesic variables, through which we have verified the consistency between the quantum dynamics of the universe wave packet and the semi-classical trajectories. Polymer quantum mechanics is an alternative representation of quantum mechanics, which is not equivalent to the standard Schrödinger one, since the continuity hypothesis of the Sturm-Lorentz theorem is violated. It can be introduced independently from the Schrödinger representation by defining abstract kets labeled by the real parameter mu, that constitute the base through which we can construct the generic cylindrical space psi. The Hilbert space is defined after a scalar product has been given. In particular, in this case, it results considering with the Kronecker delta. In this way, the orthonormality between the base states is guaranteed. Also, two main operators on this Hilbert space can be defined: the label operator that acts in a multiplicative way, and the shift operator that constitutes a one-parameter family of translational operators. We notice that the action of the shift operator is discontinuous, since the state mu plus lambda will always be orthogonal to the original state mu. And so also the set of the eigenvalues of the label operator is said to be discrete in this sense. Now let's consider a one-dimensional system identified by the coordinates qp. So the wave function of the system can be written in both the polarization p and q as reported. In particular, by considering the p polarization, we can notice that the action of the operator q is differential, and it coincides with the label operator in particular. So in this sense, it is discrete, while the action of the translational operator is this one reported here, so it is discontinuous, and in this sense we must conclude that the p operator doesn't exist. In fact, it is impossible to obtain a discontinuous operator by the exponentiation of a Hermitian one. Similar conclusions can be reached by analyzing the structure of the q polarization. In particular, the action of the operator q is discrete as well, and the p operator doesn't exist since its action coincides with the derivative of a delta function. So we have seen that if we consider the q operator as discrete, the p operator doesn't exist. So in order to deal with a well-defined dynamics, we have to regularize it. And what we do is introducing a polymer lattice identified by a constant spacing u0. We define all the eigenstates of the Q-operator on this lattice, and we restrict the action of the translational operator on the polymer lattice by fixing lambda equal to mu0. At this point, we can introduce the polymer approximation in order to well-define the action of the P-operator. In particular, since the action of the translational operator is always well-defined, we can explore the relation between the sine function and the complex exponential as reported. In this way, we can substitute this well-defined P-operator in the Hamiltonian operator in order to deal with a well-defined dynamics. Obviously, our interest in using an alternative representation of quantum mechanics in which the configurational variable is discrete in the sense that we said before, lies in the fact that, especially in cosmology, we are interested in analyzing how quantum gravity effects modifies the dynamics. In this sense, we consider the polymer representation applied to the configurational variable since often it is related to geometrical quantities like areas and volume. And as we will see below, polymer quantum mechanics represent a very good instrument for which studying and regularizing the singular dynamics of the cosmological models with a simpler mathematical framework with respect to loop quantum cosmology from which it is derived. In particular, in this work, we consider the Bianchi's first model, a cosmological model that represents the simplest generalization of the FLRW model, although still homogeneous, and so it represents a very good candidate for which studying the modified dynamics near the singularity. In this box, I have reported the classical the Hamiltonian constraint in the Astral variables that represents the variables in which loop quantum cosmology was originally formulated. In particular, the Astral connection C is related to the velocity of the scale factor, while the
Hey, Wantao.
Hi,
Hello?
Everything
what
okay?
happened?
I lost my connection, and it seems that Eleonora also lost the connection. Is that right?
Yeah,
Yeah,
because
I
we
also
were
lost connection.
everyone just
Yeah,
lost
I
the
lost it.
connection.
So let's wait for minutes because Eleonora's talk is will last to there's still 10 minutes to go. So let's wait for a while and see what's happening. If there's no response in 1 to 2 minutes, I think we'd better move to our next talk. So let's see. Sorry for the bad connection here.
I think it's better to move.
Yeah, I agree. Due to the unstable connection, let's move to our next speaker, who is Miguel Sabido. Could you share your screen, please?
Yeah, sure. Thanks. Let me start this. And so, can you see the presentation?
Yes. Take it away,
Okay.
please.
Thanks. So first of all, I'd like to thank the organizers. I had the opportunity to be at MG15 3 years ago, so this is great being here. So I'm going to talk to you about some work I've done last year. It has to do with something called gravity and its possible connection to the cosmological constant. So as already mentioned in the previous talks, there's two observations in the universe that have a little explanation. The first one is the anomalous galactic rotation curve, and of course the current acceleration of the universe. And these two problems are known as the dark energy problem and the dark matter problem. Now, currently there are some good candidates to explain these ideas. For example, for dark matter, there's a lot of work in using some scalar fields, currently known as, or more known as action fields. And in the dark energy sector, usually is more or less explained, at least phenomenologically, with the cosmological constant. Now, if one takes into account that there are some problems trying to write down complete quantum field theories for this standard model, for these particles that are not part of the standard model and that are used to explain dark matter, you also have another problem with dark energy. If you simply take the cosmological constant, we all know this great discrepancy between the observation and the prediction using the cosmological constant as the vacuum energy density. So, I mean, this is, although you can phenomenologically explain some of the aspects, at least on theoretical grounds, there's something to get a little bit worried. Now, in these approaches that I've talked about, one modifies the matter content of the universe. Yeah, so we can ask ourselves if we can modify GR to try to explain this idea. So we already seen in the previous talks that, of course, this can be done, and there's a lot of theories that try to do this. I mean, I just put 3 of those, at least for the dark energy sector. But at the first talk, we saw a whole slide with a lot of probable modified theories of gravity that can work out. So what I want to talk to you about is the following idea. So we're simply going to use an extension of gravity that has some new or different degrees of freedom, and that these degrees of freedom can account for the cosmological constant. So what are these degrees of freedom? So we're going to consider something that is called unparticles. Yes? And then using this idea of unparticles that is going to be related to something called the ungraviton, and from where we're going to talk about ungravity. And then we're going to derive the Freeman equations using some ideas of entropic gravity. I just simply using very loosely this name, basically we're using a little bit of thermodynamics. So what is an ungravity theory, or what is the ungravity theory? So it's based on the idea of unparticle degrees of freedom, which is basically that you can have, for example, scale invariant quantum field theories. Yeah, and to have scale invariance, you need to have massless particles. So the idea is to introduce a new kind of thing, which is called the unparticle, that has a continuous mass spectrum, but this allows us to have this scale invariance. So this was a lot of work maybe around 14, 13 years ago, which this extension to the standard model was, there were some experiments trying to, or using the current accelerators to see if there are any, if there's any possibility to understand or to find these unparticle degrees of freedom. So the idea presented by Goldberg and Matt was that what if we do this unparticle extension to gravity? So they work out simply for Newtonian gravity And they managed to write down an effective theory with a modification to the Newton potential. So what I'm going to try to talk to you about and to present today is to write down the modifications to cosmology induced by these unparticle effects. As I said, we'll be calling this the gravity sector. So what I'm loosely calling entropic gravity is this idea that you can use the inherent entropy area relationship. For example, this was originally done by Jacobson in 1995. We're using the Hawking-Bekenstein entropy and the first law of thermodynamics, and he derived the Einstein equation as the equation of state. And then recently, or more recently, I mean, 10 years ago, Berlin derived a non-relativistic gravity as a force that's originated again from this entropy area relationship. And so the idea is very simple. They simply take, I'm just putting the results. You can write the force or Newton's force as by following that expression, you're simply taking the derivative of the modification of the new entropy area relationship. Yeah, so in particular, if you take, for example, this entropy area relationship that we derived using some ideas on supersymmetry. But the important thing here is just to see that the entropy has the usual linear relationship with the area. When then we have a logarithmic correction that has to do with quantum corrections. And then we by hand, you can add by hand, sorry, a term that's proportional to the volume and a term that's proportional to the length. As I said, this particular entropy was derived in this paper here, in the reference. And so then you just simply write down the new force equation and then take the limit for large R, and you see that the square of the velocity is constant. Okay, so you have a flat rotation curve, which is very interesting. And then you can compare it with another modified theory of gravity that people use to understand galactic rotation curves. And you see that you can relate both of them, the A0 parameter in the Mond theory with this parameter epsilon that we obtain for the entropy. And you can see that you can have agreement with the experiment by setting down the null. So I just put this to show you that you can start with some ideas of deriving the force equation, or in another way, deriving gravity from the fundamental entropy area relationship. Now, if you go a little more and try to understand in the context of cosmology, then we can say, okay, let's start again with this modified entropy area relationship and derive the Friedmann equations. And this was done at least first when the entropy is proportional to the area. The authors in this paper derive explicitly Friedmann equations, and then they show us how to derive for more general or arbitrary functions of the entropies, which are arbitrary functions of the area. So in this case, we again take this expression, as I already presented, that depends on these terms on the area, and write down an FRW universe, yeah, described by the metric. Then take, of course, the flat case, and define this change of heat around the apparent horizon. The apparent horizon is defined as h squared plus kappa over a squared to the -1. Again, if you take kappa equal to 0 for the flat case, it's simple. Use the Clausius relation and the continuity equation, and integrate the resulting equation to arrive to what we call what is called the modified Friedmann equation. Now, it's more straightforward. You simply have to solve this algebraic equation. And what we find, at least in this simple case, in the limit that large times or large volume or large universe, and then you have a very dilute or rho totals to 0, then you find an effective cosmological constant. So what I wanted to present this is, following this approach, the fundamental object to derive the Friedmann equations, or using Jacobson's approach, the fundamental object to derive gravity, is the fundamental or the new entropy area relationship. So what we found in this result is that the term in the entropy that gives us the correct, or gives us a cosmological constant or an effective cosmological constant is the volumetric term in the entropy. So you need okay, here. So you need degrees of freedom. The scale is the volume, at least in the entropy. So again, you end up with an effective cosmological constant, and you can adjust the value of this parameter epsilon that appears on the entropy, and is of order 10 to the minus 6. Okay, so it's 2 orders of magnitude different than the number needed to explain the galactic rotation course, but I mean, it's not so bad. It's only 2 orders of magnitude. So going back to ungravity into the original idea. So talking a little bit more about the ungravity theory. So as I said before, it is simply an extension to a quantum field theory or to a field theory to add some new degrees of freedom, which have particles that have a continuous mass spectrum. Basically, we want them to be, so these new degrees of freedom can be introduced into the Hilbert, Lagrangian, Einstein. And so there, what you need to do is you start with the usual Einstein-Hilbert Lagrangian, and then add a term, which is the unparticled contribution to the graviton, or an ungraviton. In those 2 terms, the usual Hilbert-Einstein Lagrangian plus the usual matter Lagrangian plus this term that has to do with the ungravity is what is called as the ungravity theory. Now, this idea was put out in this paper it's about 10, 11 years ago. And they solved the simplest case, which is a spherical symmetry, and they found the ungravity correlations to the Schwarzschild black hole. Yeah. They also did the thermodynamics, they found the temperature, and they found the entropy. So as you can see, I mean, the first part is simply a big constant, yes? And the second part tells us that the entropy scales as the area to the parameter du. Yes. So now, and R is simply a radius, or simply a number defined between the ungravity parameters, or the parameters of this unparticle sector, which is basically the scale at which these effects appear, and also the coupling constant, which is mg. Yes, and the rest are simply constants. So at the end of the day, you can simply think that you have an entropy that scales as the area to a number du. Okay, so following these ideas that I presented before, that we can use simply as a fundamental object the new entropy area relationship, which in this case encodes the unparticle effects or the ungravity effects. I mean, you can use them interchangeably, the both words. So what we see is that, again, introducing this, using again the FRW metric, and using this new entropy area relationship, we can integrate out again as before, and find the new or the modified Friedman equations. In this particular case, I'm writing down for the parameter du equal to 3/2. And the reason I'm taking 3/2 is because if you plug in du 3/2, you get again an entropy that's proportional to R to the cube, which that means that you have a volumetric contribution to the entropy. And as before, as I said, this seems to be the terms that give us an appropriate cosmological constant. So just simply taking again the asymptotic limit for late times, we can find that we have an effective cosmological constant that depends on R. And again, remember, R is simply a combination of the Planck's mass, the coupling constant of the ungravity sector, and the scale at which the ungravity sector appears. Yes? So if we want to have an effective cosmological constant with the value needed to have the current acceleration of the universe, then we find that for example, for the black line, any combination along that line will give us the correct cosmological constant. Yes. And also, we managed to solve for different cases for this parameter du. So we have Porter, etc. And again, you can have this. These values for lambda u and mu. Now, the next idea that you have to do is then go back to accelerator physics and to see what are the bounds found for this parameter. Currently, what we found is that the results that we get for those two parameters are in accordance with the results obtained in accelerator physics. So in another way of saying it, you could think that if the cosmological constant or the current acceleration of the universe is explained by a cosmological constant, then this origin of the cosmological constant could be attributed to this ungravity sector or to this unparticle sector to gravity. So in conclusion, I mean, it's a very simple exercise and it's a very simple toy model where you can say, if I consider unparticle effects in the cosmological scenario, I can obtain the modified Freeman equations by using the mu entropy area relationship as the fundamental expression, yes? And in the late time limit, we can find an effective cosmological constant, yes? And these cosmological constants depends on two parameters. On the on the coupling constant of the ungravity sector or the particle sector with the usual quantum field theory or usual field theory, and the scale at which these effects appear. Yes. So what else can you do? So if you solve the equations not only for late time, you find that if you introduce dust, if you introduce energy, you can have at least qualitatively the correct evolution for the universe. So currently we're trying to write down to see if cosmological observations can determine the values of lambda u and mu and contrast these results with the results obtained from accelerator physics. And that's all. Thank you.
Thank you. We have time for one very quick question. Any questions? Okay. If no question, let's resume.
We have a question or a comment.
Okay.
Yep.
One is that in your paper in equation 22, you assume, and also in your talk, you assume rho is 0.
Yeah. Well, okay.
And the second comment is in the talk we were giving yesterday in a different session, we show that the data prefer delta is -2, which corresponds to du is equal to 0.
Okay, so let me see. Okay, yeah, so the lambda goes to 0. Actually, you can do, we did a dynamical system analysis, and you have an attractor. So I mean, you do have for large time this cosmological constant. And the second part of your comment, sorry, can you repeat it? Something about
we find that if you do confrontation of unparticle cosmology with data, then preferred clearly is delta is -2, which corresponds to du is equal to 0. That's the holographic limit.
Oh yeah,
which is very different from the du that you consider.
Yeah, so I mean, I just put those three cases there. So the only question for this unparticle cosmology, the only do they do the unparticle modification to the energy, to the matter Lagrangian, or to the gravity part of the Lagrangian?
Well,
because
we take the extended Friedmann equation that contains in the thermodynamic limit, the additional term t to the power 4 plus delta, where delta is 2 du minus 1.
Okay. Yeah, so I mean, I will need to check that thing. If you could send me a reference on the chat, I'll be very grateful about it.
Yes, of course, and I encourage you to look up this talk that was given yesterday in a different session, or 2 days ago, I think. And I forgot the number of the session. Do you remember?
No, it was Wednesday.
Wednesday, yeah, in the Wednesday session.
Okay, so you say lambda is did you go into zero, no? The most.
Sorry, excuse me,
okay,
gentlemen.
sorry.
I'm afraid I have to stop you. Please communicate through chat channel from the Zoom. I think we need to resume Eleonora's talk, and please share your screen. Hello, Eleonora?
Hello, can you hear me?
Yes, your talk will be 30 minutes, as I said. Please take it away.
Okay, and we'll continue from this slide. And what we study in this work is the modifications that polymer quantum mechanics introduced in the classical dynamics of the Bianchi's first model, first in the Ashtika variables. In this box, it is reported the Hamiltonian constraint in which we have used the polymer approximation for the variables Ci, since we choose to choose the variables P as discrete on the polymer lattice. And so we can solve the dynamics by solving these Hamilton equations. And as explained before, we can decouple this system and solve analytically dynamics by identifying these constants of motion, and after choosing phi as the relational time. In this graph, it is reported the trajectory of the universe volume, where the big bounce trend is evident. In particular, the universe volume has a non-zero minimum at the time p equal to 0, where the two branches of the collapsing and expanding universes are symmetrically connected. The trajectory for the universe volume has been found by combining the solutions for the variables P1, P2, and P3 in this way. And also we can calculate the critical matter energy density thanks to this formula. And it is evident from this graph that its value at the bounds clearly depends on the momentum associated to the scalar field. So we can conclude that in the Ashtika variables, polymer quantum mechanics at a semi-classical level, it is able to resolve the initial singularity introducing a big bounce, but that the dynamics described here has no universal properties. Now let's do a canonical change of variables in order to consider the universe volume itself as a configurational variable that we describe as discrete on the polymer lattice. So we use the polymer approximation for the conjugate variables eta I. And as before, we solve the Hamilton equations thanks to fixing the temporal gauge by imposing dot phi equal to 1 and by using analogous constants of motion. As before, the big bounce trend is evident from the analysis of the universe volume trajectory that is reported in this graph. But in this case, the critical matter energy density is a universal constant. If we choose K1 equal to K2 equal to K3, it depends only on fundamental constants. So in this new set of variables, the big bounce picture as universal properties does not depend on the initial conditions of the motion. Now, what is interesting to understand is whether this universal character of the dynamics is related only to the use of the universe volume itself as a discrete variable. And in this sense, the anisotropic character of the model allows us to choose another set of volume-like variables in which each one has the dimensions of a volume, but that they reduce to the universe volume itself only in the isotropic limit. Here we have the polymer modified Hamiltonian constraint. And as before, we can solve the Hamilton equations by using analogous constants of motion and after fixing the temporal gauge by imposing dot phi equal to 1. And the universe volume trajectories can be obtained by using this equation using the solutions for the variables V1, V2, and V3. And also in this case, the critical model energy density results to be a universal constant when choice Q1 equal to Q2 equal to Q3 is taken into account. So this result is quite interesting since it demonstrates that it is possible to reproduce Gaussian dynamics with universal properties only when volume-like variables are taken into account, and not only when the universe volume itself is chosen as the configurational variable on the polymer lattice. To complete this analysis, we propose a generalized version of the Friedman equation in variables V lambda 1, lambda 2 for the Bianchi's first model in the polymer formulation. Thanks to this equation, we can derive precisely the expression of the total critical energy density, and so we can highlight the critical point for the upper parameter. In fact, when studying an anisotropic model like the Bianchi1, in the right-hand side of the Friedman equation that relates the upper parameter and the energy density, we have to consider a contribution from the anisotropies that is added to the contribution related to the matter scalar field. In this sense, it is not trivial to highlight the critical point for the upper parameter, especially in the polymer formulation. Although by choosing this particular shape for the constants of motion, we were able to derive this convenient form for the Friedman equation that where it is evident the expression of the total critical energy density. In fact, it is clear that the turning point for the upper parameter it is reached when both the term related to the matter scalar field and the anisotropic term assume the value written here that is called total critical energy density, and that results to be independent from the initial conditions and the motion in this set of volume-like variables. We have verified also that this value of the total critical energy density is consistent with that one found in the previous analysis for the critical matter energy density if we consider also the isotropic term. Now, before performing the quantum analysis of this model in the Oesterreich variables, we perform an ADM reduction of the dynamics in order to deal with a Schrödinger-like equation and avoid all the issues regarding the sign of the Klein-Gordon-like probability that would derive from the Wheeler-DeWitt approach. So we write the semi-classical constraint in this way, and we solve it with respect to the momentum associated to the scalar field, and we choose the plus sign in order to ensure the positive character of the mass function. So we promote all the variables to quantum operators, and we choose to define them in the momentum representation. So the sign of C acts in a multiplicative way while the P operator is differential 1, and then we perform a substitution from C to X in order to simplify the calculations. In fact, in this way, we are able to find the solution to this equation, and in particular, we write it as a superpositional plane waves by means of Gaussian coefficients in order to deal with a sufficiently localized wave packet.
Hello, Eleonora, can you speak up a little bit because your voice is not very clear?
Okay. So thanks to this solution, we can identify this well-defined probability density that is simply the square modulus. And in the three graphs above, we have reported three different sections of the probability density. We recall that the semi-classical dynamics can be decoupled in three independent motions along the three spatial directions. So a quantum analysis based on the sections of the probability density is reasonable. We can notice that the wave packet delocalizes over time phi, but that the peaks of the probability density well follows the semi-classical trajectories. In fact, in the three graphs shown below, the red dots represent the peaks of the probability density, while the continuous lines the semi-classical trajectories that are obtained by combining the solutions for C and the relation between C and X. And we have also verified the consistency between the fit of the red dots and the continuous lines with a relative error of 1%. So in this case, we can conclude that also at a quantum level, a big bounce dynamics with non-universal properties in the Ashtekar variables is reasonable. So in conclusion, in this work, we have demonstrated that polymer quantum mechanics is able to regularize the singular dynamics of the Bianchi's first model in both the Ashtekar variables and in the volume-like ones. Also, the anisotropic structure of the Bianchi's first model has given us the possibility to use a different set of volume-like variables, and we have demonstrated that the universal character of the critical matter energy density can be reproduced both when the universe volume itself is considered as a discrete variable and also when the anisotropic volume-like variables are used. Also, we have proposed a generalized version for the Friedmann equation, thanks to which we have derived the expression of the total critical energy density in the set of variables V lambda 1, lambda 2 that results to be independent from the initial conditions of the motion. And finally, we have performed a quantum analysis of the universe with packet. Thanks to this analysis, we have also verified a good compatibility with the semi-classical dynamics. For further developments,
Eleonora, yeah, can you speed up a little bit?
Yeah, thanks to this, for further developments, a deep analysis of what it means doing a canonical transformation in polymer quantum mechanics is needed. In fact, we have obtained different physical pictures using different variables that, although are related by canonical transformations, and in particular for a proposal regarding the recovery of the equivalence between these pictures, see this preprint that is on arXiv. Thank you for the attention.
Yeah, thank you. Sorry, I don't think we have time for questions. If you have any questions, then please ask Eleonora from chat channel again. Our next speaker is going to be Simon Boudet. Please share your screen.
Good
Simon?
morning, everybody. Yes, can you hear me?
Yes.
Okay. Can you see my screen?
Yes, perfect. Thanks.
Okay.
Please take it away.
Thank you. So in this talk, I will propose a generalization of the Nyaya topological invariant to generic metric affine gravitational models. And as a concrete example, I will report some cosmological solutions in the Bianchi 1 spacetime we found. So I will first briefly recall metric affine gravity and the role of projective transformations. Then I will recall the usual definition of the Nyayan term, and then propose a generalization to the case of non-vanishing non-metricity. Then as a specific model, I will show what specific model we consider in our work featuring this new generalized Nyayan term. And in this framework, I will report some cosmological bouncing solutions together with a discussion on the behavior of null geodesics and scalar perturbations in these solutions, which turns out to be affected by some kind of singularities. So let us start with metric affine gravity, and which assumes a first order or Palatini formalism, where the metric tensor and the connection are considered as independent dynamical variables. This allows for the presence of torsion and also of non-metricity, in presence of which the connection is not metric compatible. Now, an important concept in metric affine gravity is that of projective transformations, which simply amount to a shift in the independent connection, as shown here. And we will keep in mind these projective transformations, since it has recently been shown in literature that the projective invariance of metric affine gravity models can be related to the dynamical stability of these models. So let me now recall the usual definition of the Nyayan term, which was first discovered in the context of Einstein-Cartan theory, which is defined by requiring the vanishing of non-metricity a priori. So in this context, the Nyayan topological invariant is defined in this way. And it has it is important since it finds application in several different contexts, such as in loop quantum gravity, in relation with the coupling of spinor fields, in parity violating teleparallel models, and even in the field of condensed matter physics. Now, the important property of the Nyaya term is that it can be written as a total divergence. So it is a boundary term. Now, the question is, what happens when we relax this assumption of non-metricity and we allow for a non-vanishing non-metricity tensor? Now, in that case, if we try to recover expression 4 starting from this definition of the Nyayan term, what happens is that an additional term arises, and therefore the Nyayan term as defined in this way in presence of non-metricity is not a topological term. Moreover, if we check the behavior under projective transformations, it turns out that it is not even projective invariant. Now, the first thing one can do to restore the topological character consists in defining a new Nyayan term in this way, which turns out to be projective invariant as well. Actually, we found out that it is possible to recover the two properties of topologicity and projective symmetry independently. So this can be done introducing two parameters, lambda1 and lambda2, and defining a generalized Nyayan term in this way. Now here you see the behavior of this Nyayan term under projective transformations and the expression it acquires when rewritten in this way. And you see from this that if you set lambda1 equal lambda2 equal one single parameter lambda, then you see from here that this generalized Nyayan term is projective invariant, despite topologicity be still violated by the presence of these additional terms. While if we moreover set lambda equal to 1, then this term vanish, and the generalized Nyayan term is also a topological invariant. Now, before considering a specific gravitational model, let me recall the relation of this generalized Nyayan term with usual terms adopted in the formulation of loop quantum gravity, which are the Nyayan term, and which is the one I've shown you in the previous slide, in the first slide, and the so-called Holst term, which is simply defined in this way. Both can be recovered from the generalized Nyayan term with these values of the parameters, and can be used to implement the loop quantum gravity theory, simply adding them to the Ricci scalar in the action, multiplied by a coupling constant, which is called the Mirzi parameter beta 0. Now, the Mirzi parameter is known to be related to a quantum ambiguity in the quantum theory, and this led to, in order to try to address this issue, in literature, an idea was proposed consisting in promoting the Mirzi parameter beta 0 to an independent dynamical field, the Mirzi field beta of x. And this was always done replacing beta 0 with beta of x in the action and introducing by hand a potential term, while I will show you shortly that it is possible to obtain the same result in a more natural way. So to do this, let me introduce the specific gravitational model we considered, featuring this generalized Nyayan term as one of the two arguments of a general function f. It is convenient to study the theory in its scalar tensor representation, in which is obtained defining two scalar fields, phi and beta, and introducing this potential term. So the equivalent scalar tensor theory is shown here, and you see that now we can easily identify the field beta with the Mirzi field, and in this way we can generate a dynamical character for the Mirzi field and an interaction term as well in a more natural way, without the need of introducing these features by hand in the action. Now, as you may imagine, the properties of this theory strictly depends on the values of the parameters lambda1, lambda2, featuring the generalized Nyayan term. And indeed, let me focus on this particular contraction of the field equations for the independent connection, which turns out to be equivalent to this condition, where S mu is the axial trace of torsion simply defined in this way. Now you see that if you consider the case in which lambda1 is different from lambda2, then you are compelled to set S mu equals 0. And in this case, even if the projective symmetry is broken by the choice of the parameters, no instabilities arise, since you see from this expression that the generalized Nyayan term vanishes on shell because S mu is 0 there. So it is harmless along the dynamics. And this situation is different from what analyzed in this reference, where it was shown that the breaking of projective symmetry can be related to to dynamical instabilities. So the absence of instabilities in this model is further confirmed if one looks at the effective second order theory, which is obtained substituting the solution for the whole connection back into the first order action. And you may recognize here the scalar tensor representation of standard Palatinov over gravity, where the only difference is that the potential term now depends on the Mirzi field as well. However, the equations of motion for the Mirzi field implies that it has to be considered as a function of the scalar field phi, which in turn is governed by the usual structural equation featuring Palatinov over theory, which tells us that the field phi is not an independent dynamical degree of freedom, being instead either a constant in vacuum or related to the trace of the stress energy tensor of matter. So we see from this that there cannot be new instabilities due to the presence of these additional scalar fields. Now the situation is different if one considers the other possibility, that is λ1 equal λ2 equal lambda. In this case, the effective second order theory is this one here, where we just, for convenience, reparameterize the Mirzi field via this new scalar field psi, and we redefine the potential term as well. So in this case, the structural equation turns out to be modified by the presence of this additional term, which depends on the Mirzi field and on its kinetic term, which I will call x in the following. Now, this structural equation still tells us that the scalar field phi is not an independent dynamical degree of freedom, being instead related to the Mirzi field x and t. Now, an interesting property of this model is that for lambda equal 1, and when the potential depends on the field phi alone, then the field phi is actually a function of x, of the kinetic term of the Mirzi field. And taking into account this condition, it is possible to show that this Nyayan, yeah? Can you hear me?
Yes, I can hear you.
Okay. So it is possible to show that this Nyayan model is a dynamical equivalent to the experimental compatible subclass of the degenerate high-order scalar tensor theories, which is interesting since it could provide more further justifications to those theories, which are up to now simply motivated by being the most general scalar tensor theory without Ostrogradsky instabilities. Now, as a concrete example, we looked for cosmological solutions in this model, restricting to the case in which lambda is equal to 1. And we found some bouncing solutions. In particular, we choose a quadratic correction for the model where the parameter alpha rules the quadratic term, and which corresponds to this potential for the scalar field phi, and we specialize to Bianchi 1 anisotropic spacetimes when one has one scale factor for each spatial dimension. We included matter in the form of a perfect fluid with usual equation of state. Now, introducing the volume-like variable given by the product of the three scale factors, it is possible to recast the TT component of the metric field equations in this way, in a Friedman-like equation, where on the left-hand side, we've just defined the Hubble function for the volume V, and on the right-hand side, we have a rational function of V. So here, each object appearing here is either a constant or a function of V alone. Now, this is useful since it allows to determine bounces and turning points in the volume evolution. And in particular, one has to impose the positivity of this right-hand side, and then the lower bounds of these positivity intervals can be associated with bounces in the universe volume evolution. So we checked this, and we started from the vacuum configuration, and it turns out that for negative values of the parameter alpha, there is indeed a bounce at some value of the volume VB. This is further confirmed via numerical integration of the field equations, and you see here that the volume reaches a minimum indeed, and then expands back in a symmetric branch. We note, moreover, that there is a finite future finite time singularity at some instant Tc where the Hubble function diverges. And let me note here that in correspondence of this singularity, the scale factors are non-vanishing. This will be important in the following. Now, the scalar fields instead, they relax asymptotically to constant values. The scalar field phi goes to 1, and the Mirzi field approaches a constant. This is important since in this way we can provide a relaxation mechanism for the Mirzi field, which can have a non-trivial behavior in the very primordial epoch, while it relaxes to a constant in Mirzi parameter beta 0 asymptotically. And therefore, in the late time asymptotic region, we recover the standard picture of loop quantum gravity with a constant in Mirzi parameter and without any additional scalar fields. Now we extended these solutions to the presence of matter, both in the form of radiation and of a pressureless dust. And this affects the solutions both near the bounds and in the late time asymptotic region. So let us start from the latter. And in that case, the presence of matter is able to provide an isotropization mechanism for the universe. So in particular, here you see the behavior of the degree of anisotropy A, we defined in this way. And you see that while in vacuum, it just goes to approaches a constant value. When we introduce either radiation or dust or both, then the function goes to 0 and the universe isotropizes. Regarding the region near the bounds instead, we have to distinguish between two cases. If the parameter alpha is between 0 and alpha bar, defined in this way, it's just a constant, then the solutions are not much altered with respect to the vacuum solutions I've shown you before. So I will not show them again. While instead, if alpha is smaller than alpha bar, then the situation is different. And you see here that the volume still undergoes a bounce, but there are no future finite time singularities in the volume, and the Hubble function is completely regular here. While however, the scalar field phi now vanishes at some time tc, and then becoming negative during the bounce. And let me note here the behavior of the scale factors in correspondence of the singularities at tc. You see here that now the scale factor may vanish there. So bottom line, we have two kind of solutions, and both are affected by some kind of singularities. And this is why we considered, we analyzed the behavior of null geodesics and of scalar perturbations near the singularities. So let us start from the null geodesic equation, which has a first integral in this form, where a prime denotes a derivative with respect to the affine parameter S. So you see here that potential problems may arise due to the vanishing of one of the scale factors. So if we study, for example, this situation here where just the scale factor A vanishes, then and if we assume this behavior for the scale factor near the singularity at affine parameter SC, where A0 and gamma are just constants, then it is not difficult to show that one can still have a well-behaved null geodesic and a well-defined tangent vector to the null geodesics if the exponent gamma is between 0 and 1/2. So here you see plotted the behavior of A as a function of time for different values of gamma, and while the dashed black line represents our numerical solution. So we conclude that the exponent gamma associated to our numerical solution is not in the allowed range, and therefore we are forced to disregard this kind of solutions here. While for the first kind of solutions I've shown you, remember that the scale factors are non-vanishing there, and therefore the null geodesics are well behaved. So for that kind of solutions, we proceeded further studying the behavior of scalar perturbations with modes defined in this way. And here, the function theta of t must satisfy this differential equation, where h of v is a regular function of the volume. Now you see that problems may arise if the Hubble function of the volume has a singularity, which is precisely what happens for the first kind of solutions. However, we were able to find approximate solutions near the singularity at Tc, both in vacuum and in the presence of matter. And you can see from these expressions that the scalar perturbations theta of t is always bounded near the singularity. Therefore, in conclusion, the first kind of solutions I've shown you are well behaved, both with respect to the null geodesics and the scalar perturbations. So, as a final remark, let me end with a comment. We expect to obtain a further regularization of these kind of singularities, taking into account quantum effects of particle creation, which have been shown in literature to yield additional effective terms in the Friedmann equation, which are able to further regularize singularities very similar to the one affecting these solutions. So this is the end of my talk, and I thank you for listening.
Thank you. Thank you for your nice talk. And we have time for 1 or 2 questions. And any
Sure.
questions for Simon?
Hi, Simon. I have a quick question actually. You just
Yes.
mentioned there about the D-host cosmology. Is this D-host cosmology is the general form of this D-host or some special case only?
Sorry, the DOST, the degenerate high order scalar tensor theory. That's what.
Yeah.
Okay. Yes, I have some additional details here. So these.
No,
Okay.
I
So
know
no.
about this series, but my question is are you discussing equivalence about the some special case of D-host or the complete theory of the D-host?
So if you're referring to these dynamical equivalence.
Yeah.
With those theories, okay, this also is an equivalence between our model with this choice of the parameter and a specific subclass of those theories, which is this one.
Yeah. Okay, I'm asking about this subclass.
Okay, so this is the maybe there are different notations in literature, but this is the experimental compatible subclass where F0, F1, F2 are functions of the kinetic term X. And the equivalence hold for this choice of the functions. So F2 must be our field phi function of X, and F0 must be related to the potential term of our model in this way. And moreover, this condition must be satisfied in order to have the dynamical equivalence at the level of the field equations. And this rules out the linear case. So
Okay,
that's
thank you.
there is a specific model, yes.
Okay, I will see which subclass it is. Thank you.
You're welcome.
Thanks. Please stop sharing and let's move to our next
Thank
speaker.
You, everybody.
Yep. Adria Delholm Iratore. Could you please share your screen?
Hello, yes. Give me. Okay. Okay. Hello. Can you see me and hear me and see my mouse and so on?
Yeah, that's perfect. Thanks.
And do you see the slides passing?
Yes, I can.
Okay. Let me just turn this off. Okay. Okay. So should I start?
Yes, please take it away.
Okay. So I wanted to start thanking the organizers for the opportunity to give this talk in here. And I am a last year PhD student at the University of Valencia, under the supervision of Gonzalo Olmo, with whom I developed some of this work I'm going to present here. And the idea of the talk is to try to see if there is any kind of generic effect that we could expect from metric affine gravities that we can somehow relate to non-metricity. Okay, it's not so easy to say that or to state that non-metricity is the cause of this effect directly, because it depends on the interpretation you want to give. But there is some precise sense in which you can say it, and we will see it. Okay, so first of all, let me introduce the framework. So when Einstein formulated GR, the only differential geometry that was known at the time, as far as I know, was Riemannian geometry. So it was a theory of a manifold with a metric. And the affine structure was understood as given by the metric. So they didn't know that you could formulate an independent affine structure at that time. But shortly after, Cartan developed a theory of connections. And then there arises the question of whether gravity should only be described by a metric, or on the contrary, it could be described by a metric and an independent affine connection. Okay. And if we choose the second way, what do we mean by that, and how do the things couple to the affine connection? What are the physical effects of these new ingredients? Okay, so let me just skip this quickly. So for let's say a crash course in metric affine spacetimes would be the following. So in a smooth manifold, if you only have a metric, then you can define the curvature tensor as you always know, where these are the Christoffel symbol for the metric, and you have vanishing torsion and vanishing non-metricity. Okay, this thing here. However, if you introduce an independent affine connection, which can always be done, then your curvature is now given by the Riemann tensor of the connection. Then you have torsion in principle, which is the antisymmetric part of the connection, and you have non-metricity, which is the covariant derivative of the metric. Needs not be vanishing. Okay, there's a general theorem stating that in a spacetime where with a metric and a connection, you can always split the full affine connection in terms of the connection of the given metric. Indeed, you can always do this for any symmetric to tensor. And then this n and k would be, sorry? Okay. This n and k would be 3 index tensors. N would be symmetric in mu nu, k doesn't have any symmetry. And this n would be related to non-metricity, and k would be related to torsion. They are called, I believe, this distortion and deformation, or there are several names for the n. Okay, so this theorem, I mean, keep in mind this theorem because it's quite important, because indeed, from a field theory perspective, it allows you to see any metric affine theory as a metric theory plus some bunch of matter fields which couple non-minimally to the metric. Okay, because for instance, if you have any kind of action built with combinations of the Riemann and non-metricity and torsion, then by doing the splitting, then the Riemann would be the metric Riemann plus covariant derivative of the non-metricity and the torsion plus derivative plus couplings between the curvature and the non-metricity and the torsion. And you could regard these two fields as matter fields. That's why I was not saying that you can unambiguously say, okay, if we have non-metricity, then we must have this event, because we can also interpret it just as a matter field, and with not resorting to geometry at all, and the physics would be equivalent. But it also happens with GR, at least perturbatively. So it shouldn't be any new thing. Okay, so these are the basic ingredients of the spacetime, of metric affine spacetime. Okay, well, this already I explained, and then let me summarize the ideas of the metric affine framework as opposed to the metric one. So in the metric framework, one assumes that non-metricity and torsion are vanishing. Indeed, I would say that the assumption is that there is only the spacetime is only a manifold and a metric, and the spacetime connection should be the canonical one given by the metric. But this is equivalent to going to the metric affine framework and postulating that n and k are vanishing. Okay. Then in this framework, one has a least action principle for the metric, and this gives you the dynamics of the metric. In the metric affine framework, it is the same, but one does not assume any relation between the metric and the affine structure a priori. Then one builds an action made with the affine connection and the metric, and then one uses the least action principle to find out the dynamics for both fields, given that both fields are fundamental. So one ends up having dynamics for non-metricity, torsion, and the metric in general fields. Okay. So which one is the correct framework? Well, that's for experiments to tell, of course, and there might even be degeneracies between the two frameworks. So they might not be different for all the theories. For instance, if you plug here the Lagrangian of general relativity written in a metric affine way, you end up having the same theory as metric GR, unless you couple fermions, and then you might find a torsion term that ends up being a four-fermion contact interaction and things that are already well known. But keep in mind that the difference between these two frameworks is not always easy to unveil, at least from an empirical point of view. Okay. And then, as I was saying, keep also in mind that this metric affine, any metric affine theory can always be written as a metric theory plus minimally coupled matter fields. In a work I developed recently with a collaborator, Jose Beltran, we showed that well, we show this for a particular class of theories, but then we argue in general that these non-minimal couplings to let's say the metric curvature, if one does this decomposition, they would generally introduce Gauss degrees of freedom, as opposed to some widespread beliefs on the field. Okay. So what are the motivations for considering this framework? Okay, so in a sense, it includes better the coupling of fermions to gravity, because it naturally couples them to torsion through the spin connection. And that is something that in the metric framework is banned a priori, but the fermions minimally coupled to the torsion tensor, and the result is this for fermion interaction in general. Okay, there are also some works in which it's seen that non-Riemannian features or post-Riemannian features of spacetime can heal singularities at a classical level, or at least if you want that there are non-Riemannian theories in which when the non-perturbative part of the action that deviates from general relativity becomes relevant, then which is related to the scale at which non-metricity appears, then the singularities get smoothed out. Okay, and then there is also this nice argument. I mean, it's just a heuristic argument in which one could say that one could think that non-Riemannian features could be necessary to account for some quantum gravity features if the spacetime had some kind of discreteness. Okay, so to explain this a bit better, let's say that this is gotten from an analogy with crystalline structures. So the idea is that you can describe crystalline structures in a continuum limit, and then you can describe them as basically as a manifold. If the crystalline structure is perfect and has all the atoms and molecules in their place, then the resulting manifold is Riemannian. But if it starts getting defects, for instance, if you increase the temperature and there are vacants and stuff like that, then you start like having torsion and non-metricity in the effective description. And the idea is that if the spacetime had some kind of microstructure, then maybe in some continuum limit, one can formulate the effective manifold as a manifold with torsion and non-metricity. Okay, so this is an heuristic picture that I find interesting, but there is nothing solid in this direction yet. Okay, so the first thing that the idea of testing torsion and so on is more or less already worked out, at least in GR, in metric affine GR and so on, and it has been tested in the lab with negative results up to date. But non-metricity has not been known. There's no generic physical effect that one would expect from non-metricity, or we don't know one yet. So that was my motivation when I started to do this work. Okay, so let me go to the important part. So we will first study a subclass of metric affine theories, which are described by these kind of Lagrangians. So this would be any function which is analytic and is a function of the metric and the Ricci tensor of the connection. It should be symmetrized, because if you are imposing projective symmetry, so the antisymmetric part of the Ricci would violate projective symmetry. If you don't do this, you get both degrees of freedom, as I showed with Gaussian. Okay, so bear in mind that in this kind of in this class of theories, you can find F of R theories, you can find Eddington-inspired Born-Infeld, for instance, you can find general relativity, and you can find any theory that you can build its action just using the Ricci tensor. Okay, so it's not the most general framework in metric affine theories, because you can get a lot of different terms in the Lagrangian, but it's a good point, and it will shed some light on the structure of general theories, as we will see later. So in these theories, the dynamics for the metric can be written in terms of another metric that we call the Einstein frame metric, which is related to this one, basically because it's you can think of this object as the derivative of the Lagrangian with respect to the Ricci tensor, okay? Because you only have symmetrized Ricci tensors, or let's say the derivative with respect to the symmetrized Ricci tensor. So it's a asymmetric 2 tensor, okay? It can act as a metric. Then by doing some field redefinitions and realizing that the field equations for the connection tell you that the connection should be the Levi-Civita connection of this symmetric 2 tensor, which we will call Einstein frame metric from now on, then you can integrate this equation out to solve the connection algebraically, and doing some figure definitions, you arrive to this form of the field equations, where this part in here you can always write as a function of the matter fields. So you can realize that this is just Einstein's equation coupled to a weirdly interacting matter sector. Okay, so in the end, one can formulate this theory just as GR coupled to non-linearly interacting matter. Okay, and this this in the practice, this is done through this object called Deformation Matrix, which relates the matrix in the two frames. Okay, so in general, this deformation matrix has nonlinear algebraic equations, and there are several solutions. And in these theories, if they reduce to GR in the low energy limit, then you can always find one of the branches in which this deformation matrix has an expansion of this form. Okay, this we discussed also with Jose Beltran in another paper, where we discussed that the other branches in general are pathological, but there always exists this branch. Okay, so this would be the identity, and this would be a 2 tensor, which is a function of the stress energy tensor. Okay, if you plug these ansatz in here, then you get that G would be related to Q by taking into account these terms, and then well, they would be suppressed from some high energy scale that appears in the Lagrangian and controls deviation from GR, and there would be higher order terms, of course. Okay, but bear in mind that you can write G as Q plus some terms that depend on the local energy density. Okay, so in general, because Q follows Einstein's equation, it will be the carrier of, if you want, it will be the variable that carries the spin to degrees of freedom, the massless spin to degrees of freedom. So you should think of Q as a usual metric in the sense that it encodes Newtonian and post-Newtonian corrections to the gravitational potential. So it's the part responsible to the long-range force. But the original metric also has some other ingredients which will source effective interactions in the end and are directly proportional to the local stress energy density, let's say. And then also, if you take into account the field equations for the connection and you take a covariant derivative on the left, then this is the non-metricity tensor, this is 0, and you realize that the non-metricity tensor is strictly related to all these corrections that appear here, which are corrections that are a function of the stress energy tensor. So in a sense, this part of the metric is unambiguously related to having a non-metricity tensor of this form. Okay. Okay. So this construction that I was doing here can actually be generalized for generic metric affine theories. Okay. So to sum up, consider a general action for metric affine theories, but written in this way. So this would be the action, the Einstein-Hilbert term, and this is a function, an arbitrary function of the metric and the connection. But in this function, I have stripped the dependence on the symmetric part of the Ricci from the rest of the dependence of the connection of the action. Okay, so you should think here, you should see this as a term where things that are not the symmetric Ricci appear, let's say. And these are the matter fields which I included here for generality, okay? So now one can again define a new symmetric metric by this combination. So it will be G plus the derivative of F with respect to the symmetric Ricci tensor, okay? And then one can always decompose the connection, as I was saying, as the connection for the symmetric to tensor Q plus another piece. And this other piece, if one takes into account the connection equations, should follow this equation, okay? So it should be related to this part that is not, that does not contain symmetric Ricci tensors, if you want. So then you can do all these tricks that you do in Ricci-based gravity to arrive to a formally Einstein frame of the theory. Formally it's identical to the Einstein frame in the sense that you have here GR plus another thing which does not depend on the Ricci tensor. But In here, of course, you have geometrical quantities. So this would not be what we classically understand as the Einstein frame of the theory. Okay, but you can do this in general and arrive. Let's say all the dependence on the symmetric Ricci tensor, you can eliminate it by using the equation of motion of the theory and write the action in this way, so that it is GR, and in here you don't have any Ricci tensor. So you have all the other geometric invariants, the metric Q, and the matter fields. Okay. When you go and do a perturbative expansion of these theories in terms of the high energy scale, so that was suppressing, this is suppressing symmetric Ricci terms, and this in general. Sorry.
Yeah. Hey. So sorry, you were about to be at the last minute of your talk, so please kindly just wind up it quickly.
Thank you. So this high energy scale controls deviation from GR, and basically it will source interactions in the matter sector, because you see you have here a matter field and the metric couples to all the matter fields. And this term is also related to the non-metricity tensor ambiguously, because if you have this kind of metric and you decompose the connection like this, then the non-metricity tensor is always written in this form. So you have these terms, you have this term, which would be the first order correction, and then you will have higher order correction. So one would see that you can find generic effects of non-metricity in the form of interactions among the matter sector. Okay, I did this for Ricci-based gravity, where you can see that this theta tensor, sorry, I don't know why it's not working. Okay, so in Ricci-based gravity, this theta tensor, which I was showing before, is related to the stress energy tensor. In more general theories, it can be some more general things. But let me just go to the end of the talk. So basically, we used okay, this would work. So we used self-interactions induced in electron-positron sector of the standard model, and we use data from collider experiments to constrain Ricci-based gravity theories, and in principle one could constrain general metric affine theories, or at least the coupling to the symmetric Ricci tensor of general metric affine theories, by using particle experiments. Okay, and this would be the best constraints that we have available in this class of theories, and they were improving on 6 orders of magnitude previous constraints. Okay, so if anyone has like any question or whatever about this, they can ask me or email. But I have to
thank you. Thank you for your talk, and please stop sharing. And let's move to our next speaker, Nicholas Dimakis. I'm sorry to say that I have to leave, and I pass the torch to Batul Imtiaz, who is a postdoc at our group. So thank you all. But
thank you, Wantao.
Yep, thank you. Please take over. Bye, everyone.
Bye.
Bye.
So Nikolaus, so you there? Nikolaus, you there?
Batul, I think he is not here.
Yeah, he's not here. I think we just moved to our last speaker.
Yeah.
Yeah. So let's welcome our last speaker, Igor Kanatchikov. I'm sorry.
Okay, Kanatchikov, it's me, right? Okay, so then I will just try to share my screen. Please wait for that. Okay.
Yeah, you can start now.
Okay, so I will talk about precanonical quantization of teleparallel equivalent of general relativity. Because I don't think that anybody heard about precanonical quantization, I will have to describe what I mean by that, because it is my own approach. And then I will show how it can be applied to scalar field theory very briefly, of course, and how it was applied already to the quantization of general relativity. Then I will turn to the Hamiltonian formulation, specific, the Donder-Weil Hamiltonian formulation of teleparallel equivalent of field-Bion gravity, describe its precanonical quantization, and then discuss similarities with and differences from the precanonical quantization of general relativity. So let me recall that quantum gravity is the problem of reconciliation between fundamental principles of quantum theory and general relativity. And then when we start this business, one immediately says that the fundamental obstacle is the distinguished role of time in quantum mechanics. And that distinguished role of time in quantum mechanics actually is inherited from the use of canonical Hamiltonian formalism, which underlines both both quantum mechanics, quantum field theory, and the existing approaches to the canonical quantum gravity. This formalism restricts us, the canonical Hamiltonian formalism restricts us to the globally hyperbolic space-times, and there's no guarantee that quantum gravity fluctuations would respect this topological restriction. It leads to the well-known infinite dimensionality and the lack of unique representations of canonical commutation relations. It also leads to the ill-defined Wheeler-DeWitt equation in canonical quantum gravity, the problem of times, and even to the interpretational issues with the operational meaning of the quantum states of the universe and quantum cosmology. So is there the alternative? Probably most of you would say there is no alternative. This is how we do quantum theories. But in fact, a few years after, the first papers about quantum field theory have been written by Pauli, Jordan, Born, and others, and Dirac, of course. Then the mathematicians, namely the Donder in Belgium and Weil in, I think he was already in the United States, they have developed certain Hamiltonian-like theories in the calculus of variations, which do not distinguish between space and time variables. Even Weil has written one paper in Physical Review where he proposed that this formalism could be a basis of quantization, but there was no essential progress for more than half a century after that. So what is the Donder-Weil Hamiltonian formulation? It's very easy and intuitive thing. If we have a Lagrangian function, which is function of field variables, first derivatives of fields, and space-time variables, I'm trying to introduce my notation here, so be careful. We can introduce variables which I call polymomenta, which is like canonical momenta, but defined with respect to every space-time derivative of a field. And we can define a function generalizing canonical Hamiltonian, which I call the Donder-Weil Hamiltonian function. Then in terms of those variables, the early Lagrange equation can be written in the following very appealing first-order Hamiltonian-like form, where no distinction between space and time variables is needed. So, of course, many people were thinking about it, but unfortunately, the lack of definition of Poisson bracket has prevented many of them from making next step. The Poisson bracket can be defined if one understands that the basic structure within the Donder-Weil formalism is what I call the polysymplectic structure, given by the following form of degree n+1 on the total polymomentum phase space of field variables, polymomenta, and space-time. If one restricts this polysymplectic form to this surface of initial data and integrates over it, one obtains the standard the standard symplectic 2 form on the infinite dimensional space of initial data. Then this form is maps this polysymplectic form maps horizontal forms to multi-vector fields. Horizontal forms will play the role of dynamical variables. This allows us to define the Poisson bracket. The map between forms and multi-vector exists only for very specific class of forms called Hamiltonian, which are closed with respect to this interesting product. And then one can prove that the corresponding bracket is what it leads to the Gerstenhaber algebra, which is graded Lie and graded Leibniz rule as a generalization of a Poisson algebra in mechanics. So we have some starting position for quantization. So if one make explicit calculations of examples, one can see that those forms, those brackets can be used to write the equations of motion in terms of differential forms in those brackets. And they allow us to identify the canonical variables, which are forms of degree 0, like phi n-1, and is the dimension of space-time, or forms between 2 n-1 forms, which are very simple, and all expressions which are discussed and obtained here are reduced to the standard analytical mechanics or quantum mechanics in the case when the number of space-time dimensions equals to 1. So if one applies the Dirac quantization rule to this simple Poisson bracket between n0 form and n-1 form, one can obtain the following representation in terms of partial differential operators valued in Clifford algebra. At this stage, we have to introduce a new scale of lengths, or rather volume, which I denote which I denote kappa, which has the dimension of inverse spatial volume. This is needed for purely dimensional consistency reasons, the same as more or less Planck constant is needed to represent the momentum operator as the dimensional factor. Then with a little bit of thinking, or maybe not so little bit, one can understand what is the analog of the Schrödinger equation in this case. So instead of IDT, in the left-hand side, one has the Dirac operator, which is the most natural space-time generalization of IDT to several dimensions. And again, for dimensional reasons, this scale kappa appears in the Schrödinger equation. The wave function then is the general element of Clifford algebra. It lives on the analog of the configuration space, which is the space of field variables and space-time variables. It has good conserved probability current and even satisfies it allows to show that the Dondra-Weil Hamiltonian equations are obtained as the Ehrenfest type of statement, which is a natural requirements, or at least desirable property. So if one has applies it to scalar field theory, everybody remembers what is the scalar field theory Lagrangian. So one straightforwardly obtains the expression for the polymomenta, the expression for the Dondra-Weil Hamiltonian, and with a little bit of thought, one can derive the expression for the Dondra-Weil Hamiltonian operator for scalar fields, which, as you can see, is the harmonic oscillator along the dimensions of fields. This allows, in principle, to derive the green functions, which, of course, I have no time to describe. And interesting question then would be how this description, which I call precanonical quantization, in terms of such generalization of the Schrödinger equation for a Clifford algebra valued function with the following Hamiltonian for the scalar field, how it is related to the canonical description in terms of the functional derivative Schrödinger equation with the following well-known expression for the canonical Hamiltonian operator. So the answer is that the Schrödinger functional can be constructed as a composition of precanonical wave functions restricted to the Cauchy surfaces, an explicit formula which allows to connect precanonical Schrödinger equation with the functional derivative equation is the following, difficult to digest within few seconds, expression infinite product, also known as the product integral introduced by Volterra, and such relation is valid when gamma 0 kappa goes to delta of 0, delta at equal spatial points. It shows that the quantum field theory based on canonical quantization is in singular limit when gamma 0 kappa goes to delta of 0, which is unregularized ultraviolet cutoff, if you want. So there is a certain relation, limiting relation between the results of precanonical quantization and the canonical quantization. If we apply this to generativity, and I still have to be very, very brief at this stage. So we start from the Einstein-Palatini action. Field binds and spin connection coefficients are treated as independent variables. So then we define polymoment associated with spin connection, polymoment associated with field bind variables. One can obtain the expression of the primer, the Donner-Weil Hamiltonian density, which on the surface of constraints leads to the following expression. One can see that as we have seen, there are constraints. Our brackets are defined on differential forms, so constraints are also leading to certain differential forms. One can calculate the brackets. So then it follows that the system is actually second class according to the Dirac terminology. One can introduce the following generalization of the Dirac bracket on differential forms. Interesting to see that actually one needs here to work with the observed inverse instead of the inverse. And then we calculate very simple brackets, Dirac brackets between fundamental variables. So this omega prime, those are just collections of all indices related to spin connections. I will use the same shortcut notation in my following discussion of the teleparallel gravity. And those brackets can be quantized according to Dirac, generalized Dirac quantization rule. Generalization is this density of field bind density. And we obtain, for example, the representation of the spin connect of the field bind operator in terms of the partial derivatives with respect to the spin connection coefficients. And those operators are Clifford algebra valued. Gamma underlined are flat space. Gamma matrices, gammas with Greek indexes are curved space. Gamma matrices, okay, the formula is known to everyone. And this is then the explicit expression of the Donner-Weil Hamiltonian operator. Then obviously the covariant generalization of the Schrödinger equation should be looking like that, with the spin connection matrix acting on the Clifford algebra wave function by the commutator product. This is the notation for it. And where the gamma matrices themselves are actually operators, because as we have seen, the field binds are also operators. So this leads to the following equation for the quantum gravity, for the quantum general relativity in field bind variables, better to say, where of course we have ordering ambiguities between spin connection coefficients and derivatives. And then interesting observation is that this term is actually dimensionless, which is very important, so that it can be estimated from the ordering ambiguities. We don't go more to these details. Maybe we will have time to mention them in the end. The Hilbert space here is, of course, should involve certain invariant measure on the spin connection coefficient that involves the tetrad determinant or field bind determinant, because the operators, the field binds, that's why the measure itself is operator value, which is kind of interesting, unknown, interesting feature of this formulation of quantum gravity. And the immediate bonus which we get from this quantization is that just because of the requirement of normalizability of the wave function with respect to this measure, we need wave functions which would decay at large values of spin connection. That means at large curvatures, and it means that it means the quantum gravitational avoidance of curvature singularities in this quantum formalism. The geometry of space-time in this description is described by the probability amplitude of transition from one point with certain value of spin connection to another point with another value of spin connection. So I can call it spin connection form. Okay, so what can we do now with teleparallel? It is interesting to discuss teleparallel gravity because it gives definition of energy for gravitational field, which is not trivial. It is all expected to have closer connection with gauge theories. And it is simply interesting how the quantum theory, which would be derived from the teleparallel equivalent of generativity, how it would be correlating or relating with the description of quantum gravity derived from the field bind formulation. So we start from the following action, Palatini-like action for the teleparallel equivalent, where f is the following, phi is the following linear combination of variables phi. Variables phi, there are certain definitions, and they're related with the.
Hey, I go.
Along?
Yeah. Sorry for bothering you. You have 2 more minutes for your talk.
Okay.
Yeah. Thank you.
So it is related with this quantities T, sometimes called torsion, sometimes called anholonomical coefficients. If we variate with respect to phis and tetrads, we get the system which is equivalent to the Einstein equations. So if we perform the Donderwall Hamiltonian analysis, we again get constraints, we again get the expression for the Donderwall Hamiltonian density. We define brackets on differential forms, we calculate constraints, so it becomes more complicated in this case. So when again we have to define the Dirac bracket, calculate the brackets between fundamental variables. So, for example, we immediately see that the Dirac bracket between polymomenta of f functions and with f function is not delta symbol as we would expect, but it's actually 0. So it messes things to some extent. At the same time, the coefficients f, which one could already anticipate to be related with contortion, don't commute to each other, which is very strange, unexpected. And if we quantize Dirac bracket, which we can now actually obtain representations in terms of partial Clifford-valued partial differential operators of polymomenta of functions f related to contortion in the basis of wave functions, which will be now functions of mu and field binds. So the differences of teleparallel formulation that the wave functions now on the space of on the bundle of frame on the frame bundle rather than on the bundle of connections over space-time. So precanonical Schrödinger equation is very similar, but its specific realization is much more complicated. Actually, it is not yet obtained in the closed form because this operator is not. It is clear that it is linear in DE, but I don't have yet an explicit form of it. So this is my last 2 pages. What is this that's similar to the precanonical quantized generativity constants? H, scale kappa, and Newton gravitational, they disappear from the quantum gravity wave equation itself, and they're all accumulated in the constant which is related to the reordering. Effectively, it is a cosmological constant. The description of quantum geometry in teleparallel equivalent is in terms of such correlators, y in the quantum generativity in terms of the correlations of spin connections. The measure in teleparallel equivalent of generativity is much easier to handle. It is just the multiplicative measure, not operator valued measure on the space of spin connections. The structure of constraints is more sophisticated. Both theories, this is kind of the thing to stress, both theories provide a framework for well-defined non-perturbative covariant background-independent quantum theory of gravity without ad hoc assumptions about the quantum nature of space-time, and even without interpretational issues related to the meaning of the wave function of the universe, because wave functions are just describing the statistics of quantum fluctuations of space-time, which is either quantum fluctuations of spin connection in the general relativity itself, or the quantum fluctuations of the frame field in the teleparallel equivalent. In both theories, Schrödinger equation are very similar multivariate matrix hypercomplex generalization of hypergeometric equations, and to certain disappointment, there is no obvious analog of the quantum gravitational avoidance or curvature singularity in the teleparallel equivalent of general relativity. So thank you very much for your patience and attention.
Thank you so much, Igor. So we have enough time for 1 or 2 questions. So any question or comments from the audience? I think no question or comment. So if I think there are a few comments or in the chat box as well. So there might be some discussion over there. So thank you so much, Igor, for your wonderful talk. Thank you. Thank you. Yeah. And our last speaker, Nikolaus, so he's not here. So I think we need to wind up our today's session, last session for modified gravity theories and quantum cosmology. It was a wonderful session today as well. So thank you very much, everyone, for your time and for your patience. See you guys on another conference or another webinar or next MG 17. So thank you, everyone.
Thank you very much.
Thank you. Goodbye.
Thank you. Goodbye, everybody.
Bye-bye.